Hello, this is Rahul here, back again from MySlate. In this session, we will look at some applications of derivatives, and we will begin by looking at how we can express the rate of change of quantities using the notion of derivatives. So let's get started. Let us first quickly revisit the notion of derivative, which we had discussed earlier in the videos on differentiability. So you have a look at this graph of the function that is shown here, and we recall here that the derivative of a particular function, here it's y is equal to fx at a given point, let us say x1 here. So this point on the curve is corresponds to x1 y1 here. The derivative of the function at this point is the slope of the tangent at this point, which is labeled as a here, right? And the slope is shown by this small straight line, the brown line. So the derivative implies the rate of change of the value of y, which is the function, for a very small infinitesimal change in x, right? So we write it as dy by dx when x is at x1. We can also write this in some other ways. So for example, one can more explicitly write this as dy by dx when we are at the point x1 y1, which is the same as saying that we are at the point x1, because at a particular point x1 the function takes a unique value y1. Okay, now let us look at what different slopes at different points imply. We have already seen that the derivative of the function at a particular point, let us say x1, is the slope of the tangent to the curve at that particular point. Now here we see that the slope, so let's consider these points as an example, points x1, x2, x3 and x4. And notice that the slope of the tangents are positive at points x1 and x2, the tangents to the curve of fx. So now what does that mean? So if the slope is positive, so obviously the derivatives are positive. Here x1 and at x2. At x2 we have this point b, where the function happens to cross the x-axis. So the slope being positive therefore implies that the rate of change of y with respect to the change in x, change in an infinitesimally small change in x, is positive, and therefore when x changes by a very small quantity while we are at either x1 or x2, the y changes in the same direction as x, which means that if x increases by a small quantity, y also increases at point A as well as at point B. And one can also see here that the slope is more positive at point B than at point A, right? So what that would mean therefore is that as x increases by a very small quantity, y increases much more when we are at point B than when we are at point A. Okay, and now look at this point x3 here. At x3 we can see that the curve becomes flat, horizontal for a brief moment, and therefore the slope of the tangent is 0. The tangent is flat, parallel to the x-axis, and that's the 0 slope, and therefore the rate of change of y with respect to a small change in x while we are at point C is 0. And what that means is that the value of the function y becomes constant at the point x3, which is represented by this horizontal or flat slope. Now look at this point x4, and at that point the point on the curve is this d, and the slope here is negative, right? And therefore that would imply that as x changes, y changes in the opposite direction to the x by a certain quantity. So if x changes by a small positive value, the y would decrease. That's what we mean by negative slope. And if x decreases, which means we go from right to left by a small quantity, y would increase by a small quantity. Okay, so let us now look at some real world examples where we apply these notions. For example, in your physics course, you may have come across the notions of speed and velocity. And speed we denote as dx by dt, where x is the distance traveled by an object, by a moving object, right? So when the object is at rest, we say that the speed is 0, which is the case when, as the time passes, the object does not change its position. So therefore, the distance traveled is 0. And whereas when the object is traveling at some speed, dx by dt would be positive, which implies that as time passes, the distance traveled increases. Of course, we cannot talk about negative speed, it doesn't make sense, but we can talk about negative velocity or positive velocity, because velocity, as you might recall, also implies the direction, the change in not only the displacement but also the direction. The displacement includes both the distance and the direction. And here, let us say y measures displacement of an object and t measures time. So therefore, velocity is dy by dt, if an object is moving in the forward direction, whatever that forward means, that is up to our definition. Then we say that the velocity is positive, and if it is moving in the reverse direction, it is negative. We also know that acceleration is the rate of change of velocity with respect to time. So therefore, using the notion of chain rule, we can express acceleration. Let us say acceleration is a. Let's denote acceleration by a. We can write it as, so we know that it is dv by dt, the rate of change of velocity with respect to time, the instantaneous change of velocity with respect to time. And we know that velocity could change with the distance, right? So therefore, acceleration could be expressed as dv by dx. Suppose we measure the x by displacement, right? So dv by dx, the change of velocity with respect to displacement, multiplied by the rate of change of displacement dx with respect to time. Okay. And we have seen earlier that this dx by dt, here we have used the symbol x for displacement, whereas earlier we had used y, but let's say they mean the same thing. So this dx by dt is nothing but velocity. So acceleration is dv by dx times v. And so let me rub this off quickly, just to clear the space so that we can see the next one easier. So the power, you probably also know that is the power is the rate of change of the energy use with respect to time. So here E denotes energy used or energy generated, right, depending on the context. So if it's your electronic device like your laptop or a tablet, it would consume energy as you use it with respect to time. So the rate at which it is consuming energy is what we call as power. Whereas if it is a power plant which is generating electric power, the rate at which it is generating the power would be the power that comes out of it. Economists use the notion of marginal cost, and here C represents the cost of doing something. So imagine a factory that is producing certain goods, and C denotes the cost of producing those goods from the factory, and let's say X means the volume or the quantity of goods produced. So for every unit increase in the quantity of goods produced, what is the increase in the cost of production? That is dc by dx, and that is called the marginal cost and this is also because it is derivative, it is an instantaneous notion. So what that means is that at a particular value of production, particular value of x, if the factory produces marginally extra additional quantities, then what is the change in the cost of production? So that is the marginal cost. Okay, so let us now try to appreciate this notion with a simple example. This is taken from the CBSE or the NCRT textbook. So the question is that the length x of a rectangle is decreasing at the rate of 3 centimeters per minute, and its width y is increasing at the rate of 2 centimeters per minute. So